So let's talk about my project I did here at University of Montreal, which was about improving the node selection component in branch and bound using machine learning. So yeah. I guess most of you know what is mixed integer linear programming. I will not define it, but I will motivate why it's useful. So mixed integer linear programming is useful because it allows practitioners to model any kind of discrete optimization problems in a standard way. And we can then input this form to solvers that solves the discrete optimization problem in quite efficiently nowadays. For example, the skip solver or Gurobi or Cplex, all of them are branch and bound based, and that's useful because we want to improve the component in branch and bound, which is the node selection. Okay, recall the branch and bound general framework. Given a search space, branch and bound is a search algorithm that works by recursively dividing the search space until it reaches the base case. And the base case is basically finding a very bad upper bound and already have a good feasible solution. So we can say for sure, hey, don't continue dividing this section of the search space because you will not get any better than the current feasible region. And the goal to improve branch and bound performance is to minimize this tree size. That's the idea. Of course, you can think about this worst case scenario. It just splits everything 2 exponent n. Best case scenario, it finds a feasible solution as an upper bound right in the root. And in between, we want to improve the in between. Yeah. So, as said earlier, it can be seen as a family of algorithms, not just an algorithm, because the way you decide how to partition, the way you decide which leaf to select next to partition, all of these influence the performance, and all of this has an impact on the branch and bound tree size. So how to partition, this is variable selection. Computing feasible solutions, this is primal heuristics, lower bounds, and how to pre-solve effectively, and what to dequeue from the leaves. This is what we will focus on. PS here is just the leaves in the tree. Okay. So this is just the step we will focus on improving. So there have been handcrafted approaches to this. Example of those include depth first search, breadth first search, best lower bound first search, and best estimate feasible solution score first. So I will not go into the details of what of each of these means because it's pretty straightforward, but this maybe I can spend some time. So estimate is basically computing a score, giving a feasible solution and lower bound. Given the two, it outputs you a score. If the two are close, the more the two are close, the higher the score is. And yeah, basically that's it. More details, more technical details, but I can refer to you to more details offline. Advantages and limitations of handcrafted approach. So advantages, it's already there. It's easily implementable. It's just basic algorithmics. And the method estimate is highly engineered and it's quite performant. and it is hard to beat. So it performs quite well, and it's easy to, well, it's already implemented, so why not use it? But the limitations is that even though it's highly engineered, it doesn't adapt easily to problems. Because I can give you, like, for example, if you know the optimum, you can just dive to the optimum, and that will most likely beat estimate. But this approach requires knowledge of the optimum, and by knowing the optimum, you know basically the whole problem. So it's purely adaptive to the problem. And yeah, so this gap we can use machine learning to beat skip, to make the approach more adaptive than skip, than estimate. Sorry. So the node selection, I was quite vague about what it means. I just told you, given a list of given some leaves, which one to select next. I just told you that. This is quite vague, and here we're gonna see this problem as a node comparison problem. So given two nodes, I just want to know which one is better than the other, which one leads to a, by choosing this will lead to a smaller tree size. So that's the node comparison approach. For example, deep first search given two nodes, the deepest one. For breadth first search given two nodes, the shallowest one, and so on. And for diving to the optimum, the one that contains the optimum. And we know that this is well defined because it's partitions basically. So the optimum is like in one of the partitions. Okay. So now suppose we have an expert that we want to imitate. I didn't talk about imitation yet, but just suppose we have a very good node comparison function. An expert that given two nodes, it gives you very good choice, which will lead to a very small tree size. Suppose we have such function. And suppose we only have it for training purposes because it might be very difficult to compute. It is time consuming to compute, or it may just requires already computing the optimum before solving again. So suppose we have this. For example, the expert just selects the node that contains the optimum. And so the idea is, given this, we will approximate it using tractable computation, such as GNN, such machine learning inference using the GPUs. And yeah, that's the idea. Yeah.
So when you refer to node one, like how do you characterize as a feature that node one?
That's a good question. So this, I will talk about it when I will talk about the models, the machine learning models. But for now, I can answer you that the features is just what characterizes the node. For example, the lower bound and a feasible solution in this. Those are two features, for example. Okay. Okay, before this, quick recall about supervised machine learning. So the goal of machine learning basically is to fit a model to a function. And the function, we don't know it. We just observe its behavior on a data set, basically. So you have input, you have output in the data set, and you want to approximate such function using a tractable computation, such as neural network, when you can just feed forward in use GPUs. And yeah, that's the goal. And how we do it is to minimize this thing here. And this is the probabilistic approach. It's basically, this is basically what I'm telling you here is to fit the probability distribution induced by the model to the empirical distribution, which consists of the observations you see. And for example, if you take this P model as the normal distribution with the linear mean, you get the linear regression. If you take the P model as the Bernoulli with linear mean too, you have logistic regression. And more generally, if you take the Bernoulli with not a linear, with mean not linear, but any function, this is what neural networks does. You have classification in general, probabilistic. Okay. So we're going to frame this the node comparison as a binary classification problem. Basically, this is imitation learning. Okay. So given this function P, which is the expert we want to imitate, which map pair of nodes to node, which one is better than the other. Given this, we want to sample from two distributions to get the data. We want to sample from the problem. So we want to sample instances from the problem. For example, when you solve Sudoku, you have one instance, and then you can have another instance. Those are instances of the same problem, which is the Sudoku problem. For example, traveling salesman problem, you can have different graph topologies, which are both instances of the same problem. So we want to sample from that, and we also want to sample from the branch and bound algorithm, because this is where the node comparison is made. So branch and bound iteratively asks the node comparison function which node is better, and we want to capture that. We want to capture this because this is the state of the whole basically the whole tree, the whole solving process. And so we want to sample from this. We want to sample a state from this, and then just fit the computable function, the tractable function p theta, with the untractable function p of s. Okay. An important thing here is that the branch and bound algorithm that is solving the instance I here is specified by this set of policies C. And we will see later in the experimental section what is how to choose C to basically to have data here that covers a lot of scenarios in the tree, a lot of comparison scenarios. So basically, just to give you an intuition here, we want to choose the policy C as bad as possible. We want to have the biggest tree as possible. That way we can have more data and that covers more scenarios. And we can be more robust when predicting after on evaluation mode. Okay, so now the models and the features. So 2014, first work that improved the node selection using a data-driven approach was by he and al. And they used simply a SVM algorithm, support vector machine, for the same thing, for binary classification. And the features they used was solver pseudostatistics, which, for example, includes the feasible region, the lower bound, and so on. And they didn't use too much of features. They use 20 or 30, if I'm correct. And yeah. And then 2018, Song all trained a multi-layer perception with the same kind of feature, fixed size vector features. And 2021, Yilmaz and Worksmith, limited form of neural network. So it was a specific case. It wasn't as general as the two approaches, but they did MLP as well. All of them here requires a fixed size vector for data. But we will use GNN to mitigate this issue. So our contribution with Didier here and Andrea Lodi, which is now at Cornell. We use GNN, graph neural network, as a model. So what this allowed us to do is to use this as features from Maxime Gass and also Didier paper. That's the first one that used GNN for the variable selection problem. We use basically the same features. We use this bipartite graph. On the left side, you have constraints. On the right side, you have vertices. And you have an arc that connects the both, and the arc have weight Aij in the linear constraints. And you can also characterize constraint by the right-hand side, the B, and the type if it's inequality, equality, smaller equivalent, stuff like that. You can use one-hot encoding, for example, to do that. And for variable, you have the upper bound, lower bound for each individual variable, and you have the type, continuous, discrete, binary, and also their contribution to the objective. This is important, the C here. So this is what characterizes a node. And as global vertex, we want the two. We want basically the gap. We want a lower bound and a feasible solution, and those are our features. Yeah. And see, it's not fixed size. If the problem gets larger, this gets larger as well. But you can use GNN that was trained on smaller instances, because GNN has the property that you can, like CNN, you can use them on higher or bigger graphs or bigger pictures. Okay. So the model is basically a simple GNN. We didn't do anything fancy. Layer norm, strict graph convolutions, average pool, and then we output the score. So now I told you that we want to mimic function that maps pair of nodes to a node. And here I'm just outputting a score. But still, it's not a problem because we can still compare two nodes and train basically on that. You subtract node score 1 from score 2, and you train on that, and basically you have a scoring function that you can use. So yeah, that's what I was just saying before. You take the same GNN, same weights, same everything. You feed forward node 1, you feed forward node 2, and then the function P is basically score 1 minus score 2. And with that, you can know which is better. If it's negative, then score 2 is better. If positive, score 1 is better. And you train, and now you back propagate through this, not through this. Through this, you back propagate through the whole thing. And that's it. So this is called the Siamese network architecture. Yeah. And this is basically just what you get by plugging this into the previous. And we want, as I told you before, we want to generate data from the branch and bound procedure that diversify as much as possible the samples, which are pair of nodes. And basically, then you just have this optimization problem that we solved using the Adam optimizer with weights. So why with weights? Because you see here, let's say the model make an error in this case. So the optimum is here, and the model selects this. This is a bad error. This is a very bad error because it can get the model be stuck here and lose a lot of time, while it can just select this and maybe just find the solution here and stop here without going elsewhere. So how do we penalize such kind of error? We use this. We use basically an exponential, the more depth difference there is, we put more exponential on this. This is just a heuristic. It's not, we didn't prove that it is the best we can do as a weight procedure, but it is a good heuristic and it gave us good results. So evaluation, we have evaluate on 3 problems. I will not dive into the details of all of those, but basically fixed charge multi-commodity, maximum satisfiability, and generalized independent set problem. We choose those problems because they are primal difficult, because our approach allows the solver, by improving the node selection procedure, we're basically helping the solver get feasible solutions of higher quality. So we're improving the primal side. By the diving oracle, maybe there's another kind of oracle, maybe there's another kind of expert that actually improves the dual side, but the diving improves the primal side, and we choose those to be primal difficult. So, whoops, I don't know what this is. Okay, so those are the results we obtained. You have the nodes, the tree size, basically, the time it took for the whole thing. On the left test, you have samples of the instance of the same size, of the same problem distribution. And on the right, you transfer. This is transfer learning because we're using some instances of larger size. Okay, and you can see that our approach, the GNN MLP, those are the competitors that were prior works. And we have here the skip and estimate, and you can see that the GNN beats quite consistently every other method. You can see here, yeah. So for example, reduces tree size by 46% for the fixed charge multi-commodity and 27% for JISP in the transfer setting. So that's quite good because it's larger instances, and yeah. So why, quick wrap up here, why the GNN outperforms the SVM given similar accuracies? I didn't put the accuracies here, but they were quite similar. The reason why we believe, well, I believe this is true is because simply it makes inference on the whole structure, not on solvers pseudo-statistics. But this is just an hypothesis. It might be false, but yeah. Further work, understand the theoretical limitations of this diving oracle. Maybe there's some limitations on this. And why not design another oracle that's not just dive to the optimum, but do more balanced kind of node selection to help for both primal and dual side. Yeah. And also do both, integrate data-driven node selection with the variable selection. Currently, those are doing separately. In the literature, you see variable selection alone, node selection alone, but you don't see them merge, so that would be a good thing. Okay, thank you. That's it.